Hello ladies and gentlemen, and welcome back to another screencast by your Earth Science teacher, Mr. Stano. And today we're going to go and take a look into hurricanes. This is a typical photograph of a hurricane from over above, satellite view. And there is something very, very striking that we should notice about hurricanes as we look at them from overhead. We can see one, that it has this big spiral type shape, but specifically how the spiral is. And we notice that it all going around here, this central location noticed called the eye. We can see this movement of air getting drawn into that area. We should notice that it is counterclockwise and inward, making hurricanes nothing more than low pressure systems. So at their core, their most basic form, they're nothing more than low pressure systems. They just happen to be pretty big low pressure systems and have a very high pressure gradient or very large pressure gradient in them, which contributes to the high winds that they have. Hurricanes, definitely some of the greatest storms on Earth. We've seen them with the past few that have passed by. Sandy, the year before Irene, and then just going back to Katrina, and even further back, Gloria. Massive storms. So like I said before, low pressure systems with winds blowing counterclockwise, also inward, and with speeds in excess of 75 miles per hour. Due to these winds and the extreme low pressure, they can generate 50-foot waves, sometimes more, and they are capable of causing quite a bit of damage. Some things that we need for hurricanes. We need a pre-existing weather disturbance. What that means is we need some sort of like thunderstorm, some sort of unstable air mass. We also need warm water. We'll go a little bit more into that in a moment. We need the Coriolis effect. Remember, that helps with the rotation with the wind and with the wind deflections, and consistent wind speed and directions. The tropicals, these hurricanes, like we said, they need some sort of weather disturbance, some unstable air. We need unstable air. Remember, that's air that's maybe around a low pressure zone, that's rising air. So we get these small little low pressure regions, this warm air rising. With the help of some Coriolis and rotation, we can get these to develop into low pressure systems. So if we look right off the coast of Africa over here, this is a prime spot. Here's the equator, right around here, so that we know that this, 0 degrees, is going to be relatively warm year-round. So here's our weather condition, or disturbance, and that weather disturbance will start to rotate a little bit, and it'll start drawing up energy from this warm water. Remember, warm water leads to evaporation. The higher the rates of evaporation, that water vapor goes into the air, causing that air to become less dense and rise more. Also, it's that air is going to may get heated from the warm water. So then that's going to cause that warm air also to become more or less dense and rise more. We need sea surface temperatures of 80 degrees or higher. That 80 degrees, or that warm water, really is the fuel for the hurricane. It allows that water vapor to go into the air. It allows that transfer of heat energy from the water into the atmosphere to kind of give everything that nice low density, that low pressure that we need. We see that off the Atlantic, the Gulf Caribbean, around there during June to November, which is our hurricane season, that these temperatures are roughly that 80 degrees. What we do notice is that hurricanes will lose their energy as they come onto land. Remember that land does not have the rates of evaporation that ocean water does. So that we see, or it just doesn't have that supply of moisture, such as oceans. Hurricanes need that water, and if we can cut off that access to water, the hurricane's going to weaken. So here we have this drawing right here. So we have this low pressure system. Remember, the air in a low pressure goes upwards, and what it's basically doing is it's drawing up H2O vapor from the water. So it's not the actual water, it's the H2O vapor that we're looking at, and it gets drawn up. Remember, as this vapor rises, the air is going to cool, condense. You get our cloud base right here, and when the water condenses, So when you have H2O vapor turning into H2O liquid, energy is released. So that energy is actually released into the cloud, causing that air to warm up and essentially get even less dense than it was before. So the water vapor releases energy into the environment, helping a warming effect or a heating effect on that air. And we all know that warm air carries a low density, which also equates to a low pressure. The Coriolis effect, it will help that low pressure really get it to spin. Remember that the Coriolis causes a deflection of winds over an extremely large distance because of Earth's rotation, and is what we need. So we can take these small little localized thunderstorms with the help of Coriolis, warm water. It'll cause these little systems to come together and begin to rotate as one. We also need upper level winds to have a consistent speed and direction, our jet stream, for the most part, to be moving in the same pressure as that same direction as that low pressure. What we do see is that in years of El Nino and La Nina, that it causes these upper level winds to basically become a little bit disorganized, and we'll actually see hurricanes, not as substantial hurricane season. So the stages of hurricanes is pretty simple. We start off with our thunderstorms, which are going to upgrade to tropical depressions, depressions into tropical storms. Notice our wind speeds increasing along the way. And finally, tropical storms moving upwards to hurricanes with wind speeds greater than 75 miles per hour. Some things that hurricanes don't like, or that'll cause them to basically collapse, would be moving over to colder ocean waters. Remember, warm water increases rates of evaporations, and then that water vapor goes up into the air, helping to form and sustain that low pressure when that water vapor condenses in the cloud, releasing that heat energy that it just received from the ocean, warming the system more. So we need to have warm waters. Cold waters, no bueno. It does not work out well at all. We also can move on to land. So if a hurricane moves over land, what you'll typically see is it may go from a category 3 or 4 down to a 2 or 1. We need the warm water, and we also need a constant supply of water vapor. Moving over to land does not help with the water vapor situation. It decreases the amount of water vapor. And if we have large-scale upper-level winds that are unfavorable, like I said, we'll see this during times of El Nino, La Nina, and we'll go into more specifics in class about which one's going to actually promote hurricanes and which ones will decrease the amount of hurricanes that season. These are some typical hurricane paths that we have witnessed over years. So we can see that it comes along, and it'll move and skirt the coastline and come right up. It's a very typical or average paths that we see. What we also notice is that there's a nice warm ocean current that also does the same exact thing. This is our Gulf Stream. So the hurricanes have a very similar path to what we see with the Gulf Stream. Remember, hurricanes like warm water, they like humid environments, so it would be naturally fitting that we see that it's going to try to avoid land. It's not a conscious effort, but also stay above that warm water. Katrina, a little bit different. It kind of came, bounced along, went up, over, and then moved back up into this way. But still, it's kind of hugged in. It'd like to be near this warm water. Sorry, I'm thinking about hurricanes as people, but they have some general tendencies that we always see. Here's another hurricane path. We see that one that came in and hit to Long Island quite a couple hundred years ago. See, it moved up, following the coast, moving up, and hitting our lovely area of Long Island right there. Okay, this is Hurricane Gloria in 1985. I was a mere 5 years old when this one came. And we could see, same thing. Typical path. Comes up, follows the coast. It's where it hit Long Island, comes off, and then downgrades as it goes over that colder water up north. Hurricane Andrew. Right over here. Notice the counterclockwise rotation of it. And if we look off, we see this counterclockwise rotation of another system right there. So it's common. Sometimes we may see a few of these disturbances in the water at one time. This is looking at like a composite image of Hurricane Floyd. Give you a little dimension to it. Let's see. The eye of the hurricane right here. Same thing. Counterclockwise rotation, drawing in that warm, moist air from the ocean that it's over. Okay. And since I mentioned the eye of the storm, I'll go a little bit into that now. The eye of the storm is this nice area right here. You'll see there'll be no clouds in that region. We have calm weather in there, very low wind speeds, but the winds around it are what's going to really cause that destruction. If there's no clouds in the eye, there's something else going on there. We'll talk a little bit more about that in class, but you'll just to take a note, it's very clear here in the eye. Here we go, looking at the eye of the storm a little bit closer. What we may see is that planes will do crisscross patterns over this to gather any data or measurements that they may need. And here's some information about these planes that might actually do it. We'll talk a little bit more about this later on. Okay, this is the perfect storm, which the movie was modeled after with the Andrea Gale. That was the fishing boat that left out of Massachusetts. And the members of that ship all ended up dying at sea. But you can see Hurricane Grace right here. There was a couple of other pressure systems lingering around, low pressure and high pressure, that kind of blocked everything off, helping fuel this pretty massive event. This is just a scene from the perfect storm, some of the waves generated from that. Okay. The biggest thing about hurricanes, though, are the winds and the storm surge associated with them. The winds are bad enough alone. We can see 75, gusts upwards of 100, and even higher than that, which can cause a lot of damage, like we've seen with Sandy that came through recently. A lot of trees that, if they still have their leaves on at the time, act as basically big nets, capturing that air and helping them come down a little bit easier. Another problem is the storm surge, where we have this because of the low pressure system, the weight being lifted off the water, and the winds blowing the water towards the shore creates higher tides or a higher level than water than normal. Storm surge, like I said, is that height of water that's above normal high tide. So if your high tide's normally at like a certain mark on a pier, a storm surge will make it come up higher than that. And here, this diagram will definitely help out. So we can see our normal high tide mark right here. And here's high tide. So you see it comes right up to here. During a storm surge, the wind's blowing, the low pressure system releasing or taking weight off of it will allow that height to come up and eventually pretty much go over anything that we see. And people of Long Beach definitely can remember this from last year or a couple years ago. This map right here has been developed by NOAA to basically show what would happen if we have storm surge of certain heights. So you can see along the side here, 34 feet, but we'll look at something a little bit more common between 4 and 7 feet, this blue, where it can come up towards. So all of this right here, you can see if it's a little bit higher, 22, 4, 5, 28 feet, it actually gets onto the mainland like this. So areas of Freeport, which were devastated, places on the south shore of Long Island were really devastated when this last storm came through with the extremely high storm surge. And we can take a look at here, some pictures. Some more hurricane damage, very not typical from what we saw last year. Some more damage. What we use to measure hurricanes is known as the Saffir-Simpson scale. It's a scale of 1 to 5 to classify hurricanes. And like we said, we've been basing it on wind speed, air pressure, the storm surge, and expected damage. I'm going to go right into this one here. And what we notice is that we have our category right here, 1, 2, 3, 4, 5. Notice that as the category increases, the air pressure drops. Also, storm surge is increasing, and our wind speeds also increasing. So as our category increases, air pressure drops, and also our wind speeds increase. Some precautions one should take in case of a hurricane is you want to board up windows. Remember, we're dealing with high winds. We don't need anything coming through the house and breaking glass and shattering that around. Also, you want to keep water and canned food, any supplies that you may need for a few days until things get back up and running. Because remember, power lines can go out. Know how to shut off the gas to your house. If something happens and there's a gas leak and you light a match, it could potentially cause your house to go up. You also want to be able to shut off your electric for the same reason. If there's flooding, you want to make sure that you don't have any stray sparks or currents coming around, and also shut off the water just in case a line breaks. And also evacuate if told to do so. A huge one. People in Long Beach were told to evacuate, but then it came a certain point where it was too late for some people to evacuate, and they were rendered no services because so they were on their own. So when someone tells you to evacuate, such as the governor, mayors, or local town officials, you really might want to listen to those precautions. It's annoying, and you may have to do it, but it could save you in the end. Okay. Now, as a hurricane passes, a couple of things are going to happen. Your air pressure is going to increase. It's going to go up now, which would make sense. The hurricane is a low pressure system, so as that low pressure moves off you, the air pressure is going to increase. So when we see air pressure increasing, your wind velocity decreases. That inverse relationship or indirect relationship exists. And these are hurricane names right here, going from 2002, 2007. Hurricane names get recycled about every 6 years, I believe it is. And so they have them pretty much planned out for quite a few years in advance. So you can kind of see where your name is and if it's going to show up or when it'll show up again. Some leading cause of deaths is flooding. I mean, it makes sense if these storm surges and water is coming up, that's most likely what you may die of. The deadliest hurricane was in 1900 in September, which struck Galveston, Texas. About 6,000 dead, 2,000 injured, and it is the worst hurricane in U.S. history. I believe to this date, definitely still the worst ones. And it had to do with a complete miscommunication between some local meteorologists in the area and the people not listening. And that's it. All done with hurricanes. We're going to move on to tornadoes next. Hope you enjoyed it. Take care. Have a good night.